All right, good morning, everybody. Thank you for joining us today for another educational session in our Webinar Wednesday series. If you have any questions throughout the webinar, go ahead and please type them in the chat, and then we'll go through them at the end. And I just wanted to cover a quick plug for an upcoming event that we have in Phoenix on November 3rd. We'll be having an IEQ symposium with 3 fantastic speakers and a roundtable forum. The invite will be going out tomorrow evening, so keep a lookout for that. And as you may have noticed, we are recording today's webinar, so I will email out a copy of the recording along with PDH credits by Friday this week. Today is session number 2 in our outside air webinar series that reviews another 100% outside air HVAC system concept that is gaining attention in our Southwestern region, and that is active and passive chilled beams. Dan Hani is our resident educator, and he will be our presenter today. So Dan, go ahead and take it away.
Kelly, thank you very much. And thank all of you for joining us today on 100% Outside Air Systems Part 2, a review of active and passive chill beams. My name is Dan Hani. Many of you have been with us several times in the past. I won't go into my bio information or publications or whatever. I do want to reiterate Varitec as an HVAC system solution resource. We have a presence throughout the Southwest from San Diego through Lubbock, Texas, and we can actually participate and assist in reviewing equipment and system design concepts for really any type of building that is in the market today. So whether it be a mixed air VAV system, variable refrigerant, underfloor air, 100% outside air systems, we would be happy to offer any information that we can share on moving forward with design considerations and strategies. Again, I want to reiterate, and I believe I've showed this slide a couple of times before, some of the influences on our market today that are taking place. The administration has passed the climate bill, which is adding some momentum to code revisions. In 2021, the Department of Energy announced that ASHRAE Standard 90.1 2019 will be the improves energy efficiency substantially enough that it will become the baseline performance model to be adopted by municipalities in the future. And there's language in the document, though I'm confident it will be challenged depending on the region, that this code language will be adopted within the next 2 years. So Varitec launched our technical institute so that we could be an educator and resource on these systems and evaluate projects, buildings, concepts, and opportunities on what system makes sense depending on the budget, the building design, the applications, the usage, et cetera, et cetera. Please be aware the third part of our 100% Outside Air Systems series will be held on October 26th, and it'll be on passive radiant heating and cooling systems. And per Kelly's announcement on our Indoor Environmental Quality Symposium, we are pleased to say that we have some of our nation's leading speakers on the topic, Dr. Stephanie Taylor, Dr. Mark Arith of Mayo Clinic, presenting to us on what IEQ is, its importance, and why it's gaining momentum in our building environment today. Today, however, we're going to be focusing on chill beams and 100% outside air systems. We're going to quickly review with some observations from the ASHRAE, CDC, and EPA guidelines and air quality statements. We're going to look at HVAC fundamentals and heat transfer. We're going to go right back to basics so we have a better understanding and a common understanding of why chill beam systems are more efficient than all air systems. We're going to look at and compare a conventional mixed air system versus 2 strategies of approach for chill beams, passive and active chill beams. And they're both 2 different systems altogether, 2 different building considerations on how air is actually handled within a space. We're going to then look at chill beams, product portfolio of products that are available. We're going to look at the air handlers that are used for these applications and how they're different from a mixed air system. And then we're going to propose an innovative design approach for chill beams to optimize performance even above the current practice and standards. Excuse me. So, ASHRAE, CDC, and EPA air quality statements. Let's do a quick review of some of the reasons why 100% outside air systems will be gaining probably more and more attention as we move forward. The CDC website has a subsequent statement on indoor air quality that when indoors, ventilation mitigation strategies can help reduce viral particle concentrations. Pathogens and viruses and bugs are becoming more of a consideration, especially now as we're moving into our cold and flu season. And it issues the advice to open up air dampers beyond minimum settings, as ASHRAE's Epidemic Task Force recommends. And then it goes on to say to eliminate HVAC air recirculation, which is rather interesting. The EPA acknowledges in their introduction to indoor air quality that inadequate ventilation can increase indoor pollutant levels by not bringing in enough outdoor air to dilute emissions from indoor spaces. It goes on to say that an important approach to lowering the concentrations of indoor air pollutants is the amount of outdoor air coming indoors. So that begs the question, depending on where one might live, is outdoor air more polluted than indoor air, or vice versa? Well, there are many more sources within a building potentially of indoor air pollutants than there are as recognized by the EPA and measured by the EPA. Consequently, the EPA issued this statement that studies of human exposure to air pollutants indicate the indoor levels of pollutants may be 2 to 5 times and occasionally more than 100 times higher than outdoor levels. Obviously, it's a case-by-case situation depending on the building, it's how long it's been operational and functional, etc. There's also growing concern about carbon dioxide, CO2. There's an interesting article in the June 2022 ASHRAE journal on ASHRAE position document on indoor CO2 levels. And it states, and it argues for consideration that more outdoor air should be considered because outdoor air has lower concentrations of CO2 than indoor air does. And it goes on to say that of a particular interest are several studies providing substantial evidence of acute exposure to CO2 at levels as low as 1,000 parts per million, inducing significant reductions in cognition and decision-making abilities. The federal government has done previous studies that have come up with a value of CO2 levels up to 5,000 parts per million do provide for safe environments. However, the International Space Station's biggest challenge to astronauts is CO2 concentrations and how that can result in headaches and just general sense of lethargy when at the CO2 concentrations they're submitted to. So this is an active, ongoing discussion, but we do know that ASHRAE 62.1 recommends that indoor CO2 levels be designed at 700 parts per million on the inside not to exceed 700 parts per million more than the outdoor air CO2 levels. In general, outdoors, you could see anywhere, depending on the location, of 350 up to 600 and 700 parts per million of outside air. So consequently, if you add the 700 parts per million buffer, as proposed by 62.1, you could easily have an indoor environment of 1,200, 1,300 parts per million. So this is an ongoing discussion that I want to bring to your attention because it does invite the question that maybe more outside air makes all the sense in the world to help control CO2 levels. So before we begin on chill beam systems, though, I want to make sure we have a common understanding of some certain HVAC fundamentals and heat transfer. Again, HVAC engineering purpose is to maintain building space conditions. Understand that the purpose of an HVAC system is to move energy from inside a building to outside in cooling, or vice versa in heating. And the conventional approach, of course, calculates a total building's total load. How much total load is there in a building that needs to be moved, and consequently the amount of energy needs to be supplied to allow for that energy to be controlled and removed to outdoors. So heat energy is the amount of energy present in a sample of air. And a conventional HVAC system uses air as the primary heat transfer medium. So since an HVAC system's primary function is to move energy from point A to point B, let's be aware there are two means of transferring energy. One is naturally just using the laws of physics that states that principles of imbalance always tend towards states of equilibrium. Where do we see an example of that? Well, let's look at radiation. A warm surface always radiates energy to a cold surface. It's surface to surface wherever there's an energy imbalance. We can also look at that with the forces of convection. Warm air rises, cold air falls. These are two examples of natural heat transfer that occurs as nature always seeks towards equilibrium and steady state. We can also move energy mechanically. By applying energy to a building and to a system, we can artificially move energy from point A to point B, or from inside a building to outdoors. And the purpose of these HVAC systems is to maintain thermal comfort, and that is to say, control the energy levels in a building. The second purpose is to maintain indoor air quality. How do we properly ventilate a building so that we provide good IAQ and to create a healthy, productive environment? Be aware that the total energy of a building is measured as the sum of the sensible energy in a building plus the latent energy in a building. And 1 ton of energy is equal to 12,000 BTUs. So if you hear of a 4-ton package rooftop unit, it has a capacity nominally of 12,000 BTUs of total energy at rated AHRI conditions. So what is sensible heat energy? It is the energy in the air a person senses or feels. It is the energy measured as temperature displayed on a thermostat. Sensible heat is also measured as the dry bulb temperature. What is latent heat energy? Latent heat is the amount of energy in the air necessary to maintain water in a vapor state. And there's humidity in every condition, whether it's at 90%, as we might see in the Southeast, or whether it's at 10% in Phoenix. There's always a level of humidity in the air, and it's the amount of energy present in the air that keeps water in a vapor state at that point. Latent heat is measured as the wet bulb temperature of a building. So you could say, if you want to control humidity, if you control the energy, if you remove the heat, you'll reduce the water that's able to stay in a vapor state. So what are the sensible heat loads in a building? Occupants, internal heat loads, plug loads, solar gain on perimeter walls, anything that causes an increase or decrease, or actually an increase in a thermostat. What adds latent energy to a building? What adds moisture? Occupants, humidity infiltration through perimeter walls, kitchens, sinks, restrooms, etc. Open drain pans and ceilings add to the humidity of a building. So let's look at a conventional mixed air system and how it handles the total load of a building and how it operates so that we can control a building's environmental condition. First of all, in order to have heat transfer, you have to have a heat transfer medium. And there are 3 methods of heat transfer, or 3 mediums of heat transfer available in our industry. They are air, water, and refrigerant. We need this medium so that we can transport energy from point A to point B. Air is not a dense heat transfer medium, so air can only move 0.46 BTUs per pound of air. Water is more dense, so it can move 8.98 BTUs per pound of water. And refrigerant, it's very dense and it can shift and move 88.2 BTUs per pound of refrigerant. So consequently, in an all-air system, if you're using air as your heat transfer medium, and because of air's less dense properties, you need a large volume of air to move the energy in a building to outdoors in order to maintain space set point conditions. So, and you see that total load, which is comprised of the sensible load and the latent load as discussed previously, at an air handler cooling coil. All of the load is seen at the cooling coil. That's where you see your sensible cooling as well as your latent cooling. Consequently, you need a lot of fan horsepower to move the amount of air necessary to condition and satisfy a building. Conventional systems use package rooftop units. We see them all the time. DX units, DX cooling, heat pump configurations, chill water air handlers for larger buildings. And we use these air handlers to supply 55-degree air approximately. We hope we get there with DX units in our environment, but we go to 55 so we can actually control the latent energy in the air, wring out some moisture so we can maintain humidity conditions within a building. Return air is then returned to these units and it's mixed with outside air at the air handler mixing section where it's conditioned at the coil and then resupplied to the space. But in an all air system, because air is not a dense heat transfer medium, you need a lot of duct work in order to supply that air to a building. And then you condition that building, usually per ASHRAE's design, ASHRAE Standard 55's design guidelines, to a 75-degree temperature at the thermostat. We're seeing some fluctuations now with more efficient buildings, maybe bumping that in summer to 77, 78, and in winter maybe reducing it from 72, maybe down to 70, etc. And we try to maintain a room dew point of 55.13 degrees, which is equal to 50% relative humidity at 75 degrees dry bulb temperature. And air is injected at high velocity into a space at 55 degrees to create uniform mixing in a space. Dan Inhout, previously VP of Engineering for Kruger, was adamant that a mixed air system is doing what it needs to be doing if it can maintain plus or minus 2 degrees temperature differential throughout the cubic volume of interior space. So is there a more efficient heat transfer option? What if we used chilled water to move energy in lieu of air? What if we applied the dense heat transfer medium characteristics of water? And what does that mean in an HVAC system? Why would we do that? Well, water is more dense than air, as we demonstrated in the previous slide, 8 BTUs per pound of air. The reason is, well, its density allows it a greater specific heat, which is the amount of energy required to raise the temperature of a unit mass of a substance to a given amount, usually 1 degree. Water has 4.23 times the specific heat capacity than air. So consequently, it takes less water to move the same amount of energy than it does air. And consequently, it requires less pump horsepower than it does fan horsepower to move the same amount of energy. And that is why chill beam systems are fundamentally more efficient than all air systems, because it uses water as the sensible heat transfer medium in a building. So let's look at chill beams and let's look at the overall concept and how they operate and some design considerations. One of the aspects I find very compelling about sustainable heating and ventilating systems is that instead of calculating the amount of energy required to move heat from point A to point B, it allows us to actually exploit the physical properties of heat transfer mediums and radiation to execute some of that work for us, so we don't need supplemental energy to do that. So before we expand upon this thought, let's again review total energy. Total energy, also known as enthalpy, is equal to the sensible energy in a building as measured at a thermostat, and the latent energy, the energy to hold water in a vapor state. What are the sources of sensible heat energy in a building? People, equipment, windows, solar gain, all of those items within a building. And then what adds to the latent energy? Respiration from occupants, perspiration, evaporation, and infiltration. So how can we actually shift the sensible load to a more dense heat transfer medium such as water? What if we decoupled the sensible load from the latent load that is otherwise seen as the total load in an air handler cooling coil? What if we decoupled that and then handled the sensible heat transfer with chilled water and then handle the latent energy component with the air handler serving a building? Again, to repeat, why? Because water is more dense than air, and water has 4.23 times more specific heat than air. Consequently, you can maintain a space temperature with a 4 to 6 degree chill water differential versus a 20-degree differential in an all-air system supplying 55-degree air to a room conditioned to 75 degrees. So decouple the load, decouple the sensible load from the latent load. Let's bring chill water into all the occupied zones within a building. Let's handle the sensible heat transfer local to each zone. Let's drive as much sensible energy to the chill water loop. And then we'll do the latent cooling. We'll handle the latent load, supplying the amount of ventilation air required to that building by designing the leaving air condition appropriately. And we'll discuss how to do that. If you do that, if you shift the sensible load to the chill water loop, you can significantly reduce your total airflow to a building. I'll never forget working with Henry Johnston of GLHN when he was laying out University of Arizona Environmental Natural Resource Building. One of the first things he said when he laid out the hybrid active and passive system that he was, my gosh, Dad, what happened to all my duct work? He was designing rooms depending on its application down to 0.25 CFM per square foot. We normally see about 0.3 to 0.4, maybe a little more if you're doing, well, you do more if you're serving a laboratory, but your duct work is significantly reduced. By the way, GLHN won an ASHRAE award for energy performance nationally a couple of years ago. I was really excited to hear the news from Henry when he was still, before he retired from GLHN. So again, 100% outside air systems. If we decouple the sensible from the latent load, we allow the outside air to be provided at a condition that will handle building latent cooling. We can result in systems that are of greater efficiency. And there's an added bonus with 100% outside air chill beam systems. There's no return air to an air handler. This is one of the reasons why ASHRAE was promoting on their epidemic task force to open up as much outside air as possible during the pandemic to continue flushing the building of any buildup of pathogens that occurs throughout the day. Because in order to maintain building pressure, you have to exhaust the amount of, close to the amount of air that you supply so that you maintain building pressurization. So you have a continual flushing of the building with a DOAS system. The airflow designs can easily result in 50 to 70% less airflow than a conventional mixed air system, and there's significant energy savings to be had by the reduced outside air. by the reduced amount of air serving that building. Nationally, we're seeing chill beam systems in energy modeling reports, and talking to Smith Group, HDR, and other designers, they're seeing roughly between 30 to 40% energy savings over medium pressure VAV systems. To maximize that potential, you have to have a sound design strategy, of course, and it also depends on the geographic region of the building. Is it in the southeast where there's high humidity, or is it in Phoenix, Arizona, where we have mostly a dry condition throughout the year? Passive chill beam systems offer another level of potential energy savings because it uses displacement ventilation as the air delivery solution of choice, which uses a higher entering air temperature, so you can double your economizer hours here in Phoenix, Arizona during our more temperate, drier times of the year. Again, you need to be aware of the geographical location. Arizona is perfect for chill beam systems, but we do need to be sensitive to our Arizona monsoon. I just registered a month ago a dew point outdoors of 72 degrees. Fortunately, we don't see that for days and weeks on ends. In fact, it'll even fluctuate within a 24-hour period of the day. But if you lose dew point control in a building, you can start creating some architectural and HVAC systems with condensation building up and adding to all sorts of problems to an environment. So what are passive and active chill beams? What are their design strategies? How do they work? What are some of the considerations? Again, there are two types of chill beam approaches. One is the passive chill beam approach. It's essentially a sensible cooling device only. You wouldn't want to heat in this application, though there may be unique applications for using it in the heating mode in a mixed air environment as supplemental heating. The ventilation side is completely decoupled from the chill beam. The rocket science behind this technology is a chill water coil is located in the ceiling, and we allow for the natural forces of convection to occur in a thermally stratified environment. An active chill beam is a ducted device where air is injected into a two-tiered plenum box. Air is injected into the upper tier and injects air at high velocity on opposite sides of a horizontal coil located in the lower tier. That high velocity discharge through air nozzles on either sides of the coil creates a negative pressure zone above the coil that draws room air across the coil, transferring the sensible heat energy in that space to the chill water loop where it is removed from the building. Air inlet static pressures on active chill beams are between 0.2 and 0.6 inches. Some areas you might even be able to get up to 0.7 depending on the manufacturer that you use. So let's look at passive chill beams. These are cooling only devices, and the reason being, well, if you warm air in the upper levels of the room, that warm air is going to stay in the upper levels of the room, and it'll be a long time before that energy finds itself down into the occupied zone. So what you do want to do, though, is create a thermally stratified environment where you maintain a room thermostat at 75 degrees, and the upper levels of the room will be warmer at approximately 78 to 80 to 82 degrees, depending on room load, elevation, height of that room, etc. You want to maximize the temperature differential at the beam so that you have more heat transfer. So the more heat transfer you have, the more efficient the system you have. Chill water is supplied to a passive beam coil loop at 2 to 3 degrees above space dew point. Controlling humidity in a building with a decoupled hydronic system for active and passive chill beam systems is a must. Chill water should be supplied at 2 to 3 degrees above space dew point. So if you have a room at 75 degrees dry bulb, 50% RH, you have 55-degree dew point, you want to provide your air at a roughly, or your chill water at 57 to 60 degrees to make sure that chill beam does not condense at the beam. Passive beams have a capacity of roughly 300 BTUs per lineal foot, and you have to be strategic of where you place those chill beams in a thermally stratified environment, because the forces of convection, if a beam is placed locally over the top of a sedentary occupant, could actually cause thermal comfort issues, overcool the occupant, and create a sense of discomfort. An excellent place in Phoenix, where we have high temperature perimeter walls, is to place that passive chill beam over the perimeter wall, so the heat in the convective plume off the warmer wall to the space temperature is actually dealt with at the chill beam, and that air via convection, and that cool air is then redelivered to the space via convection. Fan energy is not required. So the air side component on a passive chill beam system uses displacement ventilation. I've been involved in a number of displacement projects, very effective. Diffusers are placed low in wall, and an excellent solution is an underfloor air systems. Underfloor air systems are really developing in their capabilities of meeting building loads and needs. I didn't hear of this 10 years ago, but we are now able to lay out underfloor systems with UFAD plenum heights of 10 inches, maybe as low as 8 inches in height. So we don't need 16 inches of plenum height for an underfloor system in order to provide perimeter cooling on a building. And that's a whole other concept to discuss. So displacement ventilation is the air delivery solution of choice to create a thermally stratified environment. Here's an example of 100% outside air underfloor system with a passive chill beam at the perimeter zone. This is very compelling because you have outside air locally injected, only outside air injected in the occupied zone. And I'm confident that indoor air quality within that zone would be very, very interesting to look at and to evaluate. So how does an active chill beam differ from a passive chill beam? Well, as discussed briefly, there is an air side component. An active chill beam is ducted for airflow, unlike a passive beam. A chill beam. A conventional active chill beam has air injected in the upper tier of a plenum, as discussed, and air is supplied at high velocity on opposite sides of a cooling coil. And by providing that primary air at 55 to 60 degrees, you can actually get 1,200 BTUs per lineal foot of capacity than you can in a passive chill beam device. So these are more cost-effective solutions. They may not be as efficient as a passive solution, but we're seeing regularly 30%, possibly more, system efficiency over and above medium pressure VAV. So here's just a dynamic graphic to demonstrate how an active chill beam actually works. You can see how that high velocity airflow injected on opposite sides of the coil create a negative pressure zone above the coil, drawing room air across the coil, where it mixes again with the outside air and is supplied to the space. An active chill beam system does create a mixed air condition within the space. It is not a thermally stratified environment. Air is injected at high velocity to create thorough mixing in the room. So consequently, you're going to hopefully achieve that plus or minus 2 degree temperature uniformity throughout the actual room. To design a beam and to maximize its efficiency, you want to increase the induction ratio of room to outside air as much as possible. And that is a question of how do you select your chill beam? You really need to know how to select a chill beam. I've seen many jobs where beams are selected where the beam is designed at max GPM flow. That beam has nowhere to go if there are space contingencies that demand greater capacity. So consequently, it could compromise the performance and result in complaints of thermal comfort conditions. Design your GPM flow rate at a medium flow rate so you can either increase or decrease the chill water flow rate to increase or decrease cooling or heating capacities. Again, chill water is supplied at 2 to 3 degrees above space dew point. Active chill beams come in 2-pipe heating or 4-pipe heating configurations. I was involved in 2 articles with ES Magazine and an engineering team from Smith Group that evaluated what happens when when room dew point rises to 2 degrees above space dew point. And we discovered that for a chill beam to actually condense and start dripping in a building, it required easily 18 to 20 hours to do that. And we've got a couple of articles that demonstrate that. And we worked with our partner, Didenko, to run those tests in their test facility. How are chill beams to be piped? Well, they need to be piped in parallel. We don't want to pipe them in series. There was a design in Flagstaff that was, to my understanding, really inhibited consideration of chill beams in the future. The engineering team laid out the beams in series. You did not have the stated performance in the beams further down the line in that piping series. Consequently, the room energy levels were never satisfactorily met. Active chill beams or even passive chill beams will be designed to a flow rate between 0.6 and 2 GPM. So you need to control the amount of chill water flow to each zone. I did have a chill beam job compromised on one occasion because the design team inadvertently put a modulating valve at every chill beam. That is not required. You need 1 modulating valve per zone. Sorry about that. So what about the chill water loop to the building? Conventional designs, we normally see a primary secondary loop. The primary loop will provide 45 degree chill water to a 100% outside air unit. So you can actually provide the latent cooling you need to maintain building humidity control. And then the chiller serves a heat exchanger that will actually allow for 58, 57 degree chill water to be supplied to the chill beam loop. So that's how you decouple that. So you don't want 44 degree chill water in a space with a dew point temperature of 55. Otherwise, you will have condensation forming on the pipes and a lot of building challenges and issues. So the biggest question that we're faced with is chill beams. These are condensing devices. We don't want our chill beams raining in our building, and it creates all sorts of concern. Be aware, as with any building, the latent or the humidity of a building is driven by your supply air condition. And you have to design to dew point. And by the way, ASHRAE Standard 62.1 2019 is moving from relative humidity to dew point for design conditions on humidity. And this is a big consideration. If you provide your supply air with adequate dew point depression, you will control building humidity. Then I would argue is we often see when supplying 55 degree air off of a cooling coil of an air handler to serve and maintain humidity levels in the space designed at 75, 50% RH, especially in our dew point, in our monsoon season. I think we're going to always be challenged with that regard. So there are strategies for humidity control in a space in the event that space humidity space dew point exceeds chill water temperature. We can actually register that through an RH sensor in the space or strategically located at various points in a floor, and then do an auto temperature reset to a zone using a 3-way valve where we bleed return water from the chill beam loop back into the supply water conditions so we maintain an adequate supply water temperature to the beam to prevent condensing. To reduce the cost of valves, so we don't need a hot water valve and a chill water valve, Belimo has an excellent technology of a 6-way valve with a common actuator that should be evaluated to reduce first costs. And this just gives you a piping schematic on how a 6-way valve might be used to actually save on that water flow control solution. So what type of products are available? What type of chill beam products are available in a building? Well, a passive chill beam, as I mentioned, is just that. It is a coil in the ceiling. You can provide customized casings. So if there are architectural features you want to provide with your beam so it blends more seamlessly into the visual aesthetic of a room, we can look at that possibility for sure. But again, the technology is simply a chill water coil located in the ceiling of a room. Active chill beams, the conventional workhorse that we see over and over again because of its price point and its capacity, is Danco's ACB40 model. This is the device that was illustrated in the configurations I provided earlier. These devices can come in 24-inch wide or 12-inch wide configurations with 1-way or 2-way throw. They can be 2-pipe or 4-pipe configurations. Then the chill beam application for the Banner Health University Medical Center in Tucson, AEI was the engineer. And I'm finding this in healthcare for tighter control. They're opting for 4-pipe configuration. So we have a dedicated hot water loop serving each chill beam versus the chill water loop. And that gives a little tighter control for heating, but it adds copper and it adds first cost. So something to consider. Chill beams can come in 2-foot lengths all the way up to 10-foot lengths. And depending on the capacity and how far you drive the CFM, you can get 1,500 BTUs per lineal foot out of these beams. And in a conference room where you see wide load swings, you may want to bump the airside component to more than 5 to 10 CFM per lineal foot, maybe 15, 20, up to maybe even 35, depending on the application. But when you do that, you reduce the beam efficiency. But it is an excellent solution, providing you have a manufacturer that builds beams that are low sound at high flow rates. Then it is certainly an option for strategic zones that see occupancy density swings. Certainly is a possible solution. If you have an active chill beam mounted in in an upper level of a room that has no ceiling, it's just free hanging and exposed, you'll want to provide what are called Coanda wings in casings. Coanda wings are extended flanges along the length of the beam that allow the air discharged from the beam to establish what is called coanda, which means that it hugs the surface and is discharged further into a room to create more efficient mixing within the space. So if you do have an open ceiling and you are looking at laying out active chill beams, you'll notice that the width of these beams are much larger than a conventional chill beam mounted in a ceiling. And the purpose for that is so that we get proper dispersion of the air and thorough mixing in the environment. But be aware, there are other active chill beam solutions that could meet an architectural design. There are linear diffusers where the coil is actually vertically set within the chill beam casing. And that allows for linear discharge configuration, so you don't have a box of metal located in areas that are not sensitive to that visual potential obstruction. So there are vertical chill beams, and I'm excited about this unit. And working with PAE engineers out of Oregon and the architectural group Architecton, they embraced an entirely unique design solution for active chill beams that gave me pause when I was challenged with it. And they were, Dan, what if we turned a chill beam into a condensing device, providing we had a chill beam with a drain pan, so we could actually collect condensate during monsoon. And we effectively did that at Architecton's award-winning Helios project. All the chill beams are condensing devices in that building, and yet the energy profile and savings, because of the limited time of year we're in monsoon, made all the sense in the world. What they do in that project is that when the outdoor dew point or humidity is a certain point, they'll actually change the chiller from supplying 55-degree chill water down to 44-degree chill water to the chill beams. So they become condensing devices, and they can actually maintain space humidity. I was hesitant to embrace this concept at first, but then it dawned on me, well, what's the difference between a condensing active chill beam and a fan coil unit condensing at the coil of a fan coil unit? And providing you have drain pans and condensate pumps where necessary, you can certainly do that. So it is one innovative strategy that could be considered under unique architectural challenges, as we were faced with the Helios project. Here's another configuration of a model ACB 30 with a vertical coil supplying a linear grill in the ceiling. And then we have horizontal discharge chill beams as well, that actually can be used at perimeter zones that will throw air far enough to wash the perimeter glass, and then will provide the induction through the bottom of the unit and offer the potential for a drain pan or a catch pan. The reason why that might be considered is that if these devices were used in a lobby where you have doors opening and closing to the outdoors, then you may want a drain pan or a catch pan underneath that beam in the event humidity levels spike during a monsoon day. You certainly don't want water damage coming down onto your ceiling or down onto the floors of a building. So this is one solution for doing that. Plus, they can also be piped for condensate drains as well, and can work in that solution, in that unique application. Chill beams are very architecturally adaptable. A manufacturer that we work with, the Danco, is willing to look at custom chill beams and how they might be applied. One new technology that we have today, I don't have product literature on, but is very compelling, is a displacement ventilation active chill beam. I won't go into the details on that, but it really has attracted my attention as a very compelling idea and concept. And I just got off the phone the other day with our underfloor manufacturer. There are now underfloor active chill beam opportunities where we can actually put active chill beams at the perimeter wall of a building and push some of the space sensible load to the chill water loop to optimize performance in an underfloor system. Please be aware that if you're selecting chill beams, that the manufacturer you might be working with is certainly in intent of following their testing methodology as described by ASHRAE Standard SPC 200. I was actually a voting member on that committee. And what it does is it does for chill beams what AHRI does for chiller and coil performances. It standardizes a testing methodology so that everybody can rest assured that the performance published by those manufacturers are based on that testing methodology and not of some invention of their own. So talking about chilled beams, let's move on to the air handler component. These are not just air handlers on a roof. I've been challenged in the past with, well, that's an expensive air handler. Well, you're right. They're not as competitively priced as a conventional medium pressure VAV air handler. Why is that? Well, for one thing, we have to make sure that we're adequately conditioning the outside air. Your dollars per CFM, depending on the size and CFM of the unit, it could range anywhere from $10 a CFM to $15 a CFM on a custom unit. You can also use a semi-custom design as well that offers a lower price point if you go with a semi-custom unit by the various manufacturers out there. Anyway, these 100% outside air units, because we're supplying 100% outside air, those buildings also require that we exhaust that building from the air. Well, we don't want to take all that conditioned space air and then just dump it outdoors. So a DOAS unit is a dual tunnel unit that puts a heat recovery wheel in the unit that actually preconditions the outside air before it sees the cooling coil, with the exhaust air leaving the building. There are two types of heat recovery solutions. There's sensible only, which comprises of plate and frame heat exchangers, or you could do a sensible only wheel. And then there are enthalpy wheels that actually do meet some of the latent capacities in preconditioning the outside air, as well as the sensible. So we always see heat recovery devices in a 100% outside air unit. We can put chilled or hot water coils. We've found a very compelling technology is what can be done now with DX 100% outside air units through our manufacturers, using variable speed compressors for tight control of air conditions, dehumidification, and leaving air conditions. We want to make sure the unit is properly filtered, but if you provide a 100% outside air unit, it does beg the question, do you need MERV 13 filtration and the inherent static pressure penalty paid on fan energy for that enhanced filtration? Well, you have no return air back to a building, so the answer is no. You want to design the DOAS to meet as a minimum the ventilation requirements for that building as defined by 62.1. But remember, 62.1 provides minimum outside air requirements, not necessarily best outside air requirements to enhance building IAQ. What is the air change rate of outside air to a building necessary to secure good indoor air quality? Well, I'm hearing through ASHRAE, though I validated last week with a 62.1 board member, that though there are many studies going on right now assessing what is a good air change rate, nothing has been definitive yet, and we don't know what that is. We're going to hear probably a good design will require 2 to 3 air changes per hour. Optimally, I've read as much as 4 to 6. Regardless, there's an energy penalty for that enhanced outside air. So you want to make sure you have the heat recovery solutions in place to reduce the load on a cooling coil at those outdoor air flow rates. Dedicated outdoor air units for active chill beam systems will provide 55 to 62 degree supply air. If you provide higher than 62 degrees, you need to make sure you are adequately dehumidifying the air at the cooling coil. A passive chill beam DOAS unit is unique because I can actually supply 62 to 68 degree air out of a passive chill beam DOAS unit. Again, providing the coil is properly selected and we're getting the dehumidification necessary to depress the supply air dew point. But what's attractive about this is that if you can supply 65 degree air to a building versus 55 degree air, in Maricopa County, you can move from maybe 17% annualized hours operating in economizer mode and double that to maybe 34 to 35% of the annualized hours of a year in our dry, temperate climate months of between October, November through to March, April. So be aware of the difference in the DOAS configuration between a passive and an active chill beam system. And here are some considerations that give you an idea of how these dual tunnel units look like. Fan wall technology is certainly available, so we can optimize fan performance, heat recovery across a coil that is always seeing a uniform velocity across the full coil face. And a lot of solutions we can do with air handlers. And again, there are semi-custom configurations, custom configurations, different price points that we would see. Traditionally for chill beams, we would see chill water, but I think we might even want to consider looking at packaged DX solutions with variable speed compressors. And the reason why I say that will be addressed here shortly. And one of the best kept secrets in the industry is discrete use of desiccant dehumidification to maintain dew points at a proper level. It's a passive dehumidification solution that certainly is very attractive and gives you great control of your building humidity levels. So if you do use a DX solution for your DOAS, and you can decouple the DOAS unit from a chill water loop, so you only have one primary chill water loop serving a chill beam system, that chill water would be supplied at 55 degrees instead of 44 degrees. So what does that mean with regard to chiller technology? Well, working with Daikin, we did an evaluation on the new air-cooled Pathfinder chillers, and we found out that the EER of a chiller supplying 44-degree chill water in our design environment with 18 condenser fans has an 8.0 EER. If you actually provide 55-degree chill water, your EER and IPLV levels bump, so you get added chiller efficiency by supplying warmer chill water temperatures, and you can design the DX DOAS to a low enough dew point supply air condition where you can provide tight building latent control as well. So 100% outside air systems, active and passive chill beams. Just a quick review. Active and passive chill beam systems are more energy efficient because they reduce system horsepower. You have opportunities to maximize free cooling, certainly with a passive system and doubling your economizer hours. You increase operating efficiency. These systems, because of the reduced ductwork, significantly reduced ductwork, lend themselves to lower floor heights, smaller mechanical room footprints. So there's some real estate advantages architecturally to be aware of. And what's also very attractive is if a chill beam system has no fan motors to consider, no filters to change out. These are just dumb boxes that are meant to last 20, 30 years that sit in a space, and the only operating piece is the modulating chill water, hot water valves, providing chilled and hot water to the chill beam device. So there's some significant life cycle cost to consider when applying a chill beam system. These systems are inherently silent. You don't have high velocity discharge air whizzing above your head or going through a variable air volume box when at part load. And also because they're 100% outside air systems, they offer the promise of superior IAQ, a topic that we're going to be challenged with in considering in greater detail here in the not too distant future. The potential drawbacks of chill beam systems are many contractors are unaware of the system, haven't installed them. The first cost estimates are such that they can offer a first cost premium. Also, you have additional plumbing associated with it. And another thing to consider is the additional cost of a tighter envelope. You need to make sure that the perimeter wall has a vapor barrier or certainly a good air barrier configuration so that you reduce the humidity infiltration on a monsoon day, high humidity condition, because humidity will always go from wet to dry, and building pressurization will not stop humidity infiltration from the outdoors to indoors. So you need to be aware of a tighter envelope to assist in controlling humidity to the space. And then, of course, you want to make sure to control humidity that you have supply air design at the appropriate dew point. So that is our presentation for today. I thank you for your time in joining us. I hope I've brought a deeper awareness of how active and passive chill beam systems work, why the principles that determine why they are more inherently efficient, and the benefits a building owner has in reduced operating costs and the possibility of superior indoor air quality. Thank you very much.
All right, so I do have a couple questions in the chat, but before I get to that, everybody please look at your chat and see if you have a message from me, because if you do, then I can't figure out who you are and how to give you credit if you need it. And then also, I sent out a poll in the middle of your presentation, Dan. I don't know if it popped up on your screen or not, asking how many people have designed or installed shield beams before.
Oh, okay.
So out of the 52 people that responded, only 10 said yes.
Interesting.
Yeah, so I just wanted to share that number with you.
Thank you.
All right, so the first question, what are typical airface velocities out of an active chilled beam?
We normally see, depending again, it depends on the amount of outside air, depending on the application, but we would see anywhere from 120 to 150 feet per minute.
Okay. And how do you clean those condensate pans? It looked like those horizontal chilled beams were mounted in hard lid.
They were mounted in hard lid. If you design using an active chill beam, well, first of all, let me make a distinction. The photos of the vertical active chill beams showed what are called catch pans. They were not condensate pans per se, they're called catch pans. So if you do hit a high dew point condition in a room and condensation occurs, which by the way, it takes hours. We've got the articles and the test findings from the DANCO to support that. But if it occurs, it's caught by that pan. You don't have a pool of water that you would find in a conventional condensate pan. But if you did plan on using it as a condensate device or a condensing chill beam, you'd want to have the means for actually cleaning out that drain pan over time. There's no question about it. Treat it like a fan coil unit.
Okay, yeah, I think that question came in when you're talking about the Architecton project where they were reusing the condensate. Yeah,
I think they had panels in the ceiling, if my memory serves me correctly. The whole design team was on board on the need of the condensate pan. So I'd be surprised if those panels were not available for access.
Okay, and then with the high face velocities, is noise ever an issue?
Actually, yes. Noise is always a consideration for active chill beams because you're faced with the challenge of well, we want to reduce the cost of the chill beams as much as possible. Okay, well, the way to do that is to enhance performance. How do you enhance performance? Increase the airflow. Well, let's increase the airflow to what a chill beam can do. And consequently, you can enter into a sound issue when you hit plenum pressures of 0.6, 0.65, 0.7 or above. I don't recommend it for many manufacturers out there. We have a manufacturer that is very attractive at high airflow rates in their sound, but we normally design chill beams to about an NC value of about 17 to 20. They're very quiet devices, even though they're served by a primary duct at 1/2 inch of static pressure. It all depends on how you select the nozzles.
All right, that is all the questions that we have in the chat.
Okay, well, thank you very much. And Kelly, were we going to be opening up a blog opportunity on chill beams on the Varitec website?
Yep, so actually last week I posted a blog about chilled beams, so you guys can all go take a look, along with the record. It's all on by Friday. I'll send out all the PDH certs, along with a link to our website that will have the recording, any educational backup documents that Dan referred to, and then also that blog post will be in there as well.
Yes, if you're an AIA member and you're looking for an HSW credit, please email Kelly your AIA number and we'll make sure you get that credit. I enter myself.
Yep, unless you registered with it and I know what your name is on the screen, then I already have you down. But if you did not register with your AIA number, then email me.
Excellent.
All right, thank you so much, Dan, and thank you everybody for joining us today.
Thank you for joining us today.